So we've already covered the dot product, which is one form of vector multiplication, but there's a second one, the cross product. And I'm just going to warn you, the cross product is actually kind of a weird operation when compared to the dot product, because we're working with all these numbers and we've already seen the dot product, which gives us a scalar as the result. But the cross product gives us a vector, which is a little bit strange. So you're multiplying two vectors together and you get a vector. And the book defines the cross product as the product of the magnitudes of two vectors, we're going to keep A and B, and the sine of the smaller angle between them. And it's written out as A cross B, which is how it's said. So if you ever hear myself or an instructor say A cross B, this is what you look for. I'm going to ignore that little first term right now. So it's the two magnitudes times the sine of the theta between the angle, or between the vectors. And that should look very familiar. That looks almost like the dot product, except for it's a sine instead of a cosine. But we have this additional unit vector. And what this a hat n unit vector does is it gives us a vector instead of a scalar. That alone can cause some problems in terms of computation, which we're going to use as our motivation to find a second definition for the cross product. As previously saw in a video that was placed in this playlist deriving the commutativity of the dot product, we saw that the dot product was commutative. And a bulk of it relied on the fact that there was a cosine term for the theta. So in the geometric meaning, cosine theta is equal to cosine of negative theta. That's just a trig identity. And what that meant is that A dot B is equal to B dot A. The cross product, however, depends on a sine term. And we know from trig that sine of theta is equal to negative sine of negative theta. So we can't say that it's purely commutative. Instead, we have to put on the little restriction that says if you want to flip the order of the cross product, you have to slap a negative sign in front of it. So one of the most common ways to think about this is with a right-hand threaded screw, which I'm hoping some of you have messed around with. And you've actually had to screw things together. And if it's right-hand threaded, right turn is a tight turn and left turn is a loose turn. And it's because when you turn it to the right, it goes into the wall. When you turn it to the left, it comes out. So think of A cross B as going from turning your screwdriver from the A vector to the B vector. And in our image, that's from A to B is a clockwise turn, so to the right. What ends up happening is the screw actually plunges into the surface. But if you were to flip the order, and this was purely commutative, what that would also say is that if you were to turn to the left, it would also go down into the plane, which isn't true. Instead, what happens is if you turn your screwdriver to the left counterclockwise from B to A, the screw actually comes up from the surface. So that's how you unscrew something. How can we use this in terms of manipulating unit vectors and seeing the interactions between them? And we started doing this with the dot product, seeing how these unit vectors interact. And we're going to keep focused on our rectangular coordinate system. Let's actually look at the relationship between a hat x, a hat y, and a hat z really quick. They're all perpendicular, right? And if we use our right-hand rule, which we've been using so far in this whole lecture set, we know that if we apply a cross product from a hat x to a hat y, so putting your index finger along a hat x, your middle finger along a hat y, and your thumb will point in the resultant vector. There's your cross product. It results in a hat z. And you got to make sure that you use your right hand. But if you can actually manage to contort your hand around without breaking your wrist, I don't want to see anybody coming into class with a wrist brace on because of it, you can actually see that a hat z crossed with a hat x is going to give you a hat y, and a hat y crossed with a hat z is going to give you a hat x. And you can kind of see this. So for example, the a hat z crossed with a hat x, you're kind of taking your screwdriver and turning it from a hat x or a hat z to a hat x. And if you almost curl your hand or move your hand in that direction too, your right hand, your thumb is going to be pointing towards a hat y. Looking at these images and using these relationships, when you look at the unit vectors, we actually kind of get this cyclical pattern which arises with the cross product. So if we were to line them up and let's say we have a cross product a hat x crossed with a hat y, we can actually go along in a circle, and you would see that it's a hat z. And it's linked together kind of like an integer ring, it's linked together. But we're going to call clockwise the positive direction. So if you have a hat y crossed with a hat z, you just keep going in a clockwise direction, and you're going to hit a hat x. So that's a pretty cool way to remember it. But what happens if you go the other way? So let's say we have a hat y crossed with a hat x. If you go to the left, or if you go counterclockwise, it's negative. So if you go clockwise, it's positive, counterclockwise, it's negative. So a hat y crossed with a hat x will give you negative a hat z. And this cyclical relationship, this little image here, a little bit more refined and not kind of scullied, tomatoey looking diagram, should be drawn on your cheat sheets, because this is an easy way to remember the relationships instead of having to write down every pair. It's a pain. If you remember this and you write it down in your cheat sheets, it's a lot easier to remember. So what about the rest of the pairs? Well, you can use your right hand rule, you can use the circle, and kind of using both of these, you could actually write out the relationship between each one of the rectangular unit vectors. But kind of like we mentioned in the dot product, you can't forget about a unit vector crossed with itself. Since the angle between a vector crossed with itself, A crossed with A, the angle between the two vectors is 0. They're the same vector. There's no difference. So we have 0 as our theta, sine of 0 is equal to 0, the cross product is equal to 0. So how can we use this relationship and all the relationship between the other rectangular unit vectors to actually find an alternate definition to help combat against the difficulty of finding that normal vector and that angle? So what we do is we take our A vector and our B vector and we break them out into components again, and just like we said with the dot product, it's multiplication. That means it's distributive. So what ends up happening is we break out our A cross B into 9 different terms that are summed together. And just like with the dot product, we group together the components and then the vectors being operated on together. And you can start going through these vectors and using the circle and things that we talked about, actually find what each of those cross products will actually result in. So for example, a hat x crossed with a hat x. Well, we know that's already going to be 0. What about a hat x crossed with a hat y? It's going to be a hat z. But a hat x crossed with a hat z, now we're going in that counterclockwise direction. So we know that it's going to be negative a hat y. And continuing through this, we can once again separate out everything that survives the cross product, and we can actually break them out into terms that have an a hat x, a hat y, and an a hat z. Now you may be thinking, oh great, now I got to write this formula down on every cheat sheet, and I got to write down, this is just going to be such a pain to memorize. Well, if you look at the way that it's formed, there's a specific operation that you should have learned in linear algebra that if we utilize, it has the same result. And that's the determinant. We can actually write the cross product in determinant form. So what this means is that we write A cross with B is equal to, you put all your components on top. So a hat x, a hat y, and a hat z. Then you put your A vector on the second row and the B vector on the third. This is really important. It has to go components on the top row with first vector, so A, and then B. It has to be in that order. If not, you're going to get a different answer. So this is where you're going to get very, very thrown for a loop, and people are going to start losing points on problems, is they're not going to remember how to properly calculate the determinant. And there's some tricks to it and things like that, but if you really need a refresher, there are a lot of online resources which talk about the determinant, and you've been through MEA, and hopefully you still have your notes. And hopefully you were awake enough and aware enough that you actually took good notes on how to take the determinant. But otherwise, this is the most common way to determine the cross product.